Okay. Yeah, you can start. Om Namo Venkateshaya. A very good afternoon to everyone. I am Dr. A. Vidyullata, working as Assistant Professor in the Department of Mathematics of Sri Padmavati Women's Degree and PG College, run by Tirumala Tirupati Devasthanam, Tirupati from Andhra Pradesh. First of all, I want to thank the officials of Center for Professional Development in Higher Education, University of Delhi, for making me a participant of this worthy refresher course in mathematics, operational research, statistics, and computer science. Today, we are coming almost to the end of the 6th day of our course. And in the past 4 days, we have learned many new things from the eminent resource persons. This afternoon, I feel it's a great pleasure for me to introduce the speaker of this session, a very senior mathematician, Professor S.C. Arora ji. Namaste, sir. Dr. S.C. Arora.
Namaste.
Dr. S.C. Arora ji is a retired professor from the Department of Mathematics, University of Delhi, residing in Delhi. He is 75 years old with 48 years of rich teaching experience. He worked as a lecturer in Hansraj College, University of Delhi for 20 years, worked as reader in the Department of Mathematics, University of Delhi for 10 years, and as professor for 12.5 years in the same department. He also worked as professor in applied sciences at PDM Group of Institution, Bahadurgarh, Haryana, for 5 years, and as HOD and director at SGTP Institute of Management and Information Technology, New Delhi. His academic qualifications: he did his BSc from the University of Delhi in 1965, got first division and secured second position in the university. MSc from the University of Delhi in 1967, got first division and secured first position in the university. He pursued his doctoral degree from the University of Delhi in 1975 with research topic operator theory. He has 46 years of rich research experience with 108 research papers published in national and international journals of countries like USA, Australia, Japan, Romania, Italy, Germany, South Korea, Bulgaria, Croatia, China, Malaysia, Poland, Iran, etc. To his credit, he wrote a book, a textbook of calculus, published by Pitambar Publishing Co., Delhi in 1984. Under his research guidance, he has guided a total of 75 students, among them 53 are for MPhil and 22 are for PhD. He has a great administrative experience as head department of mathematics, Delhi University, member of board of studies of many Indian universities, member of DRC of MDU, B.R. Ambedkar University, Agra, member of advisory committee of Trinity Institute of Higher Education, Delhi, and many more. He has organized many national and international conferences at the Department of Mathematics, University of Delhi. He attended various national and international conferences, including IMS conferences and Indian Science Congresses held in India. He visited Dubai and Oman on CBSE assignments, delivered a talk at international conference in Bulgaria, visited Bhutan in the year 2007 on university assignment, delivered lectures at various schools of Delhi, colleges of Delhi University, and in management institutes associated with GGSIP University. He worked very actively and contributed in various academic bodies like Central Board of Secondary Education, National Council of Educational Research and Training, State Council of Educational Research and Training, Indian School Certificate Examination, UGC, DST, UPSC, Jammu and Kashmir Public Service Commission, Himachal Pradesh Service Commission, Jharkhand Public Service Commission, Bihar Public Service Commission, and DRDO, and also Kendra Vidyalaya Sangathan, and many more, like IIT Delhi also. He delivered many invited talks at various workshops and conferences, and a few of them are History of Convergence and Recent Advances, Mathematical Logic and Applications, Convergence from Ancient Times to Present Ages, Real versus Complex Analysis, Logic versus Fuzzy Logic, Boolean Logic, etc. Sir, today we are eagerly waiting for you to hear you, sir. I welcome you, sir, to present your talk on Path of Convergence, sir. Welcome, sir.
Thank you. Thank you very much for all the nice words that you have used to me.
Thank you, sir. It's a great pleasure
I do
for
not
me,
know
sir.
how to justify by. Thank you very much, for all the nice things that you said about me. Well, my topic of discussion at the moment is convergence from ancient times to present ages.
Okay, sir.
Well, before I begin with the talk, I was just trying to recall. You see, when I took admission in MSc class,
yes, sir.
In the year 1965. In
yes,
fact,
sir.
I passed in 1967. Well, a teacher was teaching analysis, and he was talking about at that time that every infinite bounded set has got a limit point. See, every infinite bounded subset of real numbers has got a limit point.
Yes, sir.
I remember that I asked him a question. Sir, can you give an example of an infinite set? He was surprised. He said, set of natural numbers, and that is an infinite set. Why I am trying to recall, you see that incident, because at that time, it was difficult even to imagine an infinite set. That is actually the thing. I am talking of 1960. Well, he talked about a problem. I'm audible?
Yeah, audible, sir.
Audible? And no problem?
Audible, sir. No problem.
He tried to
no, it's breaking, sir.
a problem that there is a race between hare and tortoise, and suppose tortoise is given a head start, say after some distance, whatever may be speed. Suppose that the hare is moving, say, his speed is its speed is 10 times, but still he gave an argument that suppose the position of the tortoise is B and the position of hare is A, and by the time hare moves to tortoise, the tortoise will move further, and again by the time the hare occupies the new position of the tortoise will move further, and so on. So that amounts to that hare would never be able to overcross tortoise. Well, then he asked, where are the problems? The problems I am telling you was the concept of infinite set in the ancient times that was not known. That was the problem. See, to talk about those infinite sets, to talk about that the infinite number of real numbers can be added up, it was difficult to imagine. So, this is in that context, when we are talking of those times, when we try to imagine which one is the most the initial mathematics. And if we try to talk about those persons of you know uh, old times, they did not have any place to live. They used to live in open and used to sleep in open, and they try to look at the sky, and they try to see the stars moving from this place to that place and so on. These are the things. And that led to the initial mathematics was the astronomy. People used to go for hunting, used to come back in the evening, did not know how many of them had gone, and because the number system was not there, he, and how many had come back, what they designed, they while going for hunting, they used to put stones, each one for one's self. And after coming in the evening, they used to pick up stone. And if some stone were left, then they could conclude that some person is missing. Of course, how many they did not know because the number system was not in existence. This is what led to the development of mathematics. This is how mathematics developed. The word convergence, of course, because infinite sets were not known, so the question of convergence did not arise. But that came later on when infinity number of real numbers were added, when the number system came into existence, and infinite number of real numbers were added. And so then that led to so-called the convergence of series, and then by see that outfits of convergence, uniform convergence, etc. See my talk, because I'm supposed to deliver two talks. The initial one, the first one is the history of convergence, from where the word convergence came, who talked about, which way it came, which way the mathematics got developed. In my first talk, I will talk about ancient times and the discussion that was done in ancient times regarding mathematics. And in my second talk, of course, I will go a little further, talking about the weak convergence, strong convergence, and convergence in major spaces. That is what I will do. So the first one is more or less it is historical, but I will keep on explaining whatever is required. Of course, I have prepared the talk, the first one, because it is more descriptive. Mm. So uh, yes, the first one is history of mathematics and convergence. Mathematics holds the mirror up to civilization. It is no exaggeration to say that the history of mathematics is the history of civilization, because as civilization got, as he developed, it developed along with mathematics. If you want to know which society is, what is the level of development of a particular society or particular so-called city or particular country, see the level of mathematics they are trying. If the level of mathematics is high, then the civilization, they are developed the proportionality. So it is no exaggeration to say that the history of mathematics is the history of civilization. Mathematicians can take pride in the fact that their science, more than any other one, is an exact science. Mathematics is an exact science, in fact. We do not talk of vague things, we talk of exact things. and that hardly anything ever done in mathematics has proved to be useless. The geometry of the Greeks and the arithmetic of the Hindus are as usual and admirable as any research of today. Accounts of the origin of Greek mathematicians center on the so-called Ionic and Pythagorean schools and the chief representatives of each, Thales and Pythagoras. See, the year is 640 to 546 BC and 585 BC. With Thales begins the study of scientific astronomy. This is what the initial mathematics I told you. It began with astronomy. Of course, other things got attached to it, and then further developments that came into it. But initially, because people didn't have anything, they used to see the people of Stone Age. They used to look at sky. They used to look at river. They used to look at sea and clouds, etc. eh? And this led to so-called astronomy. And then further, eh, people like Kepler, laws of planetary motion came, because they used to look at planets. And when the planets it started, when the planets, the motion of planets, they noted, and this is how astronomy got developed. What is really known about the life and work of Thales is very little indeed. His birth and death are estimated from the fact that when he predicted a solar eclipse in 585 BC, probably he was in his prime, and say about 40, and that he was said to have been 78 when he died. During the last half of the 5th century BC, there circulated persistent and consistent reports concerning a handful of mathematicians who evidently were intensely concerned with the problems that formed the basis for most of the later developments in geometry, astronomy, philosophy, and language. This period is called the heroic age of mathematics. Mathematics got developed along with this age, they called heroic age of mathematics. There were seven men architects, and these 7 men are there: architects of Tarantum, 428 BC, Hippasus of Metaponantum, 400 BC, Democritus of Abdera in Thrace, 460 BC, and Hippias of Elis, 460 BC, Hippocrates of Chios, 430 BC, Anaxagoras of Cleza Minen, 428 BC, and Zeno. Zeno is more important because we will discuss him a little more. Zeno paradoxes, they were very famous at that time. Zeno of Elia, 450 BC, called the seven wise men who contributed to tackle mathematical problems of fundamental nature. About Zeno, it was said, whatever you say, he will prove that to be wrong. Because he used to give arguments, the one which I was discussing here in Terratite, this was one of the paradoxes that Zeno gave forward. The Eleatic philosopher set all his contemporaries guessing by propounding his following 4 paradoxes: the dichotomy, the Achilles, and the arrow, and the state. This Achilles is that here and Terratite. The first paradox argues that before a moving object at a given distance, you see, please see, look at the paradox. The first paradox argues that before a moving object can travel a given distance, it must travel half its distance. When we see that half distance, then it must travel half of that distance. Then again, the second one, the third one, third half, fourth half, sixth half, seventh half, which is the first distance which it will travel. That was not known. That was the first paradox. But before it can cover, it must travel the first quarter of this distance and so on. That is what I am telling you. And before this, the first eight and so on throughout an infinite number of subdivisions. So the runner wishes to get started must make infinite number of contacts in a finite time, but it is impossible to exhaust an infinite collection. Hence, the beginning of the motion is impossible. Look at what he proved, that a moving of the motion of and moving object was impossible by this argument. Where is the where is lapse? What is that is missed? What is that is missed? That he is growing, that an object which is to move cannot move, but it is moving. But by the arguments he is giving, he says that the motion is impossible. In any case, I'll come to all three, come to the explanation of this paradox. In the second paradox, an Achilles is racing against a tortoise. That is what I was mentioning. I mentioned in the beginning that has been given a head start, and it is argued that Achilles, no matter how swiftly it may run, it can never overtake the tortoise, no matter how slow the tortoise may be. By the time that Achilles will have reached the initial position of the tortoise, the latter will have advanced some short distance. And by the time that Achilles will have covered this distance, the tortoise will have advanced somewhat further. And so the process continues indefinitely, with the result that the swift Achilles can never overtake the slow tortoise. You must notice one thing in each paradox. It is the infinite continuum that is appearing, and infinite sum that is appearing. And that infinite sum, what that comes to be, that infinite sum comes to be, that was not known at that time, and therefore there was the confusion, and therefore these paradoxes were possible. This is what the crux of the whole situation is. In the third paradox, it is argued that a moving arrow is always at rest. Again, see, a moving arrow is always at rest. In the arrow, Zeno argues that an object in the motion instant equal to itself, but that which occupies a space equal to itself is not in motion. And this is true of every instant. Hence, the flying arrow is at all times at rest, so that its motion is an illusion. He says that motion is not, and that's only illusion, motion is not there. Most controversial of the paradoxes on motion and most awkward to describe is the stadium. The fourth paradox stated as follows. Look at this paradox. See, let A1, A2, A3, A4 be bodies of equal size that are stationary, and let B1, B2, B3, B4 be bodies of the same size as that of A's, and but they are moving to the right, so that each B passes each A in an instant, the smallest possible interval of time. Let C1, C2, C3, C4 also be of equal size with A's and B's, and let them move uniformly to the left with respect to the A's, so that each C passes each A in an instant of time. Assume that at a given time the bodies. In any case, I begin with this paradox, fourth paradox. Suppose let A1, A2, A3, A4 be bodies of equal size that are stationary, right? Assume that. And let B1, B2, B3, B4 be bodies of the same size as that of A's, which are moving to the right, so that each B passes each A in an instant. And the instant is the smallest possible interval of time. In the smallest possible interval of time, the uh, the motion of each B is there. Let C1, C2, C3, C4 also be a equal size with A's and B's, and let them move uniformly to the left with respect to the A's, right? So that each T passes each A in an instant of time. Assume that at a given time the bodies occupy the following relative position. This was the first position. But when they move, because B1, B2, B3, B4 will move to the right, and C1, C2, C3, C4 will move to the left, right? Then after the lapse of a single instant, that is after an one instant, after an indivisible subdivision of time, the position will be as follows. This would be the position, right? The first instant. Thus, it is clear then that C1 will have passed two of the B's, and hence the instant cannot be the minimum time interval. For minimum, again, when we try to search out, we are not able to find out which is the minimum time, but minimum time required for the passing one of those bees. But every time it moves two times, the will have passed two of the bees. Hence, the instant cannot be the minimum time interval, for we can take as a new and smaller unit of time it takes C1 to pass one of the bees. That will never be possible. But look at all these four paradoxes if you examine. We observe that practically these things do not happen because these are only paradoxes. But where is the problem? We must not imagine that Zeno and all the wise men who argued the point failed to recognize that these were only paradoxes. And in reality, the things happen otherwise. These are only paradoxes, but the things happen otherwise. But where is the problem? What troubled them was, where is the catch? The difficulty was the horror of the infinite, because infinite was difficult to imagine. Horror of the infinite, it was difficult to imagine any infinite set, which I began with the question which I asked in my MSc previous class to my teacher. Sir, can you give an example of an infinite set? Because it was not it was very difficult to imagine infinity at that time. Just even 50 years back, a student like me who were finally, of course, topped the university in 1967. But at that time, it was difficult to imagine an infinite set. And I asked this question. I admit, I asked this question to my teacher. Sir, can you give an example of an infinite set? The, the difficulty was the horror of the infinite, the infinitely many addends, that how to add infinite number of, say, real numbers. It was difficult to imagine. The infinitely great sum, the infinite divisibility of magnitude. That you see, if you take a line, the line is constituted of points. But how many points? Difficult to imagine. The infinite divisibility of magnitude, a misconception that a sum of infinitely many addends is always infinitely large, because that is what we used to imagine. That is what we used to conclude, that any infinite number of real numbers will go to infinity. What is infinity? Not known. I remember I asked while teaching cardinality to my students at MSc level, or say even at BSc level, when I talked about cardinality and ordinality, I asked, can you define an infinite set? The immediate answer was that a set which is not finite is infinite. And then I asked, okay, can you define a finite set? A set which is not infinite. This was, we at that time, if you talk any ordinary person not knowing mathematics, for him, any set which is not finite is called infinite, and all sets have same infinities. For them, any finite set is infinite, and all infinite sets have same number of elements. This is one who does not know cardinality, etc. For him, the any set which is not finite will have infinite number of elements, and all infinite sets have same number of elements. So in any case, the infinitely many addends, the infinitely great sum, the infinite, see, these things were unknown. Assuming the infinite divisibility of magnitudes in an answer of Zeno paradoxes came out the Greeks, the solution was actually presented by uh, Greeks to all these paradoxes, because it says, if from a given magnitude, a magnitude not less than half is subtracted, and from the remaining one, a magnitude not less than half is subtracted. If this process of subtraction is continued, then in the end, there remains a magnitude less than any pre-assigned magnitudes of the same kind. Do you know what does this mean? This means if from x you take away x by 2, and from x by 2 you take away half of it, means x by 4, and from x by 4 if you take away the x by 8, and from x by 8 if you take away x by 16, and so on, then what is left is, that is nothing. Do you know what it means? This means 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 4, and so on, so on, so on, so on, is equal to 1. This is what, see, if you see mathematically, this one, if from a given a magnitude not less than half is subtracted, and from the remaining one, a magnitude not less than half is subtracted. If this process of subtraction is continued, then in the end, there remains a magnitude less than any pre-assigned magnitude of the same kind. Mathematically, it means this thing. Mathematically, it gives you the foundation of so-called convergence of series. This ancient exhaustion principle in the modern time is this, that if r is greater than or equal to half, and that is less than 1, then from any m and for any epsilon greater than 0, there exists some m such that m into 1 minus r raised to power n is less than epsilon for all n greater than or equal to m. Meaning thereby that limit of the concept of limit in the present time, that the exhaustion principle amounts to this thing: limit of m into 1 minus r raised to power n tending to infinity. This is equal to 0 for all r greater than or equal to half and less than 1. Visually speaking, if you see, you apply exhaustion principle to this square now. Please see. You take a square of the length of each side is suppose 1. You are taking away half of it. See the lower, see this one, left half. Left half, you are left with this triangle here. See, half of it is left, and from this half, you take away again half of it. Then you are left with this one, and then again you divide into half, and so on. If you keep on repeating and repeating and repeating and repeating, then you take away the whole square. Nothing is left. The method of exhaustion was first used by Antiphon 430 to 430 BC, whereby he exhausted the area between a circle and an inscribed polygon. The this is foundation of so-called integral calculus also. The method was put on a more scientific basis by Eudoxus 370 BC, who compared the curve and the straight line configuration. This was used by B06 BC in his famous book Elements to show that the area of two circles are proportional to the square of their diameters. But it was Archimedes 225 BC who made the most elegant use of the application of the method of exhaustion and who came near to actual integration. This was so called, as I told you, the foundation of integral calculus. Now, when you try to find out the area under a curve and the length of any curve. For this reason, perhaps the method of exhaustion is sometimes erroneously attributed to Archimedes. A problem on the borderline, a problem on the borderline of number theory and geometry was the relation of points on the line segment to the line segment itself. What exactly was the magnitude of a point and how many of these would make up the line segment? Look at, see a paradox of this type. You see, if you consider any line, and if you give some length to any point, I was talking about three general periods in the development of infinite series. The first period was the period of Newton and Leibniz, that of its introduction. Second period was the period of Euler, the formal stage. And the third period was the modern period, that of scientific investigation of the validity of infinite series. These three periods I was talking about, and I was telling that the third period, am I audible? Am I audible?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay. The third period began with the year 1812, when the first important and strictly rigorous investigation of series was made by Gauss. This is what I was trying to mention. When he discussed this series, 1 plus alpha dot beta by 1 dot gamma into x plus alpha into alpha plus 1, beta into beta plus 1 over 1 to gamma into gamma plus 1 into x square and so on, designated as this. But you see, as happens with every development in the beginning, whosoever develops is in the beginning, he is completely ignored. See, nobody pays attention to him. But then later on, it is realized that it was an important development. That happened with Gauss also. Owing to the strangeness of the treatment and unusual rigor, Gauss paper excited little interest among the mathematicians at that time. Then, more fortunate in reaching the public was A.L. Cauchy. This is photograph of Cauchy, 1789 to 1857, who wrote a book entitled Course D Analysis. We will discuss Cauchy little more, because he made a mistake in the beginning. A man like Cauchy also made a mistake in the beginning, but later on it was corrected. In the year 1821, containing rigorous treatment of series, the book was designated for students of Polytechnic and was considered a fundamental treatise on analysis. A.L. Cauchy in the year 1821, as mentioned, wrote a book entitled Course D Analysis. The following theorem appeared. See, I am talking of Cauchy's famous wrong proof because he made a mistake. Cauchy made a mistake in the beginning, and he proved that every series of continuous function converges to a continuous function. This was the mistake that he proved. A convergent series of continuous function converges to a continuous function, which you know is not true. See, now we know why, because it is only and not just convergent only. See, it is uniformly convergent only, then it converges to a continuous function. But a man like Cauchy also made a mistake and talked about that a convergent series of continuous function converges to a continuous function. Following Cauchy fairly closely, the arguments mentioned were the following. He considered a convergent series of continuous function whose sum is the function s, the nth partial sums of this series be denoted by Sn and Rn be the remainder. At any particular value of the variable x, Sn is continuous in the neighborhood of the particular value of x in the question. Consider the increases that these are these three functions receive when one increases by x by an infinitely small quantity. The increase of Sn will be for all values of n an infinitely small quantity, and that of Rn will become insensible at the same time as Rn if one assigns to n a very considerable value. Hence, the increase of the function s can only be an infinitely small quantity. From this, one deduces immediately the theorem of Cauchy. See, this is what it says. In Cauchy proof in the modern language, the proof runs as follows. If whatever is stated, you see, if we talk about mathematically, this is that epsilon greater than 0 be given. Then, since each function is continuous, their partial sum s and x is continuous, and therefore there exists delta greater than 0, such that for every a with a mod less than delta, s n x plus a minus s n x mod is less than epsilon. And since the series converges at x, this means there exists capital N, such that for every n greater than n, Rn x mod is less than epsilon. And since the series converges at x plus a also, there exists, taking the maximum of these two, there exists n, and this n is common because we have taken the maximum. For every n greater than n, Rn x plus a mod is less than epsilon. Then making this calculation, s of x plus a minus sx mod is less than, hence the some function s is continuous, which of course you know. But in 1826, a Norwegian mathematician Niels Abel actually, you know, you have done Abel theorem, etc. Same Abel. eh? 1802 to 1829. The most, I think, this, uh, 1802 to 1829. The most outspoken critic of the old methods in series wrote about Cauchy's theorem as, it seems to me that the theorem admits of exception. Along with this series, he considered this series sine x minus sine 2x by 2, etc., where all the terms of the series were continuous, but the sum function of this series is discontinuous one. This series converges at each x, but the sum function is discontinuous. In mid 19th century, in the year 1847, a student of Dirichlet, namely Philip Seidel, encouraged by the following phrase, when a proof is wrong, he says, do not just abandon it, but analyze it carefully to see if there are any hidden hypotheses that would make it correct. Analyze the proof carefully as follows. He says in step 1 of the proof, we need to realize that delta depends upon epsilon x and n. We write it as delta x epsilon x n. In step 2, n depends upon epsilon and x, so we write n epsilon x. However, in step 3, n depends upon epsilon and x and also on a. Using the same notation, we express this as n epsilon x plus a. To make Cauchy's proof work, we need an integer m bigger than n epsilon x and also bigger than n epsilon x plus a for each a, satisfying a mod less than delta which depends upon epsilon x and n. Thus, we must know that m, which is maximum, this exists for all epsilon. That is, that m does not depend upon x. Consequently, the additional hypothesis that we need is that for every epsilon greater than 0, there exists m such that for every n greater than and equal greater than m, and for every x r and x mod and less than epsilon. What is this? This is nothing but uniform convergence. This, in fact, is nothing but uniform convergence, and is precisely what is needed to make Cauchy's theorem correct and the proof work. What is required? The requirement is that it is not just convergent series of continuous functions is it converges to a continuous function, but it has to be uniformly convergent. That is what was the discussion. That is what was pointed out in Cauchy's that wrong proof, and it was pointed out that whatever you are saying is not correct one. It has to be, this additional assumption has to be made so that the proof can work. So that it has to be uniformly convergent series of continuous function that converges to a continuous function. See, however, before Seidel, Stokes and Cauchy had analyzed the topic of uniform convergence. The property had been used extensively by the young Weierstrass, 1815 to 1897. Already in 1838, in a paper on elliptic functions, Weierstrass teacher Guderman used the phrase convergence in a uniform way. This word uniform convergence earlier was used in this way, convergence in a uniform way, etc. The names kept on changing. Ultimately, now the accepted name is uniform convergence. When the mode of convergence of a series is independent of the variable phi inside. He thought it is a remarkable fact that when an infinite series converges in a uniform way, but he did not give an exact definition, nor did he use the property in the proof of any theorem. Now, this is Carl Weierstrass, who probably learned about the concept in Guderman's course on elliptic functions in 1839 to 1840, coined the term, this one, the German uniformly convergent, used it in a critical way in his 1841 paper. The paper name is there, where he showed that if a series of analytic functions converges uniformly in a connected domain, its sum is analytic, and one can differentiate term by term. However, since this paper remained unpublished, the mathematical world did not know and learn about the essential use of uniform convergence until he began to lecture at the University of Berlin in 1856. The concept of uniform convergence was only a small piece in its complete refoundation of analysis. This is how the development of convergence came, and finally, you know, this was all about the history of so-called convergence, uniform convergence. Any question you would like to ask? In the present time, the concept of convergence and uniform convergence, etc., um, that can be read in the modern times in various ways. Of course, I have chosen a selected few only. That I will talk of weak convergence, and I will talk of outfits of uniform convergence in major spaces. These two, in the present times, I'll discuss. Although the lectures can be delivered on uniform convergence, convergence of series, etc., etc. And many it can be read, it can be discussed in various ways. The first one I'll talk about is weak convergence. I'll discuss weak and strong convergence in non-linear spaces. I'm sure everybody knows what is a non-linear space. You see, linear space over the set of complex numbers. I have a linear space over the set of complex numbers, and uh, norm is, of course, a map from the set X. Suppose X is a linear space. A norm is a map from X to the set of non-negative real numbers, satisfying that this is a map X going to X norm, and X norm is always greater than or equal to 0 for every X. Alpha into X norm is equal to alpha mod into X norm. See, and X plus Y norm is less than or equal to X norm plus Y norm, and X norm is equal to 0 if and only if X is equal to 0. With this, it becomes a non-linear space, and we are considering the set of complex numbers, not real. If if the field is the set of real numbers, then it is a real non-linear space. But we consider X to be a non-linear space over the set of real numbers, no, complex numbers. Well, every non-linear space is a metric space with the metric dxy with the metric d defined as dxy is equal to x minus y naught. Since it is a metric, therefore all those topological notions also come into existence. The Cauchy sequence, convergence, etc. And every completeness to every complete non-linear space is a Banach space. Now, come to the convergence part. We take a sequence xn in the set x. X is a non-linear space. We take a sequence xn. We say we can define two types of convergence. Although these are not the only type of convergence that we can define. We can talk of weak star convergence, etc., and other things also can be talked about. But we will discuss only weak and strong convergence. A sequence xn is said to converge weakly to x in x if for every f in x star. What is x star? X star is the adjoint conjugate space of the space X. That is the set of all bounded linear functionals on the space X. If for every f in X star, that means f is a map from X to the set of complex numbers. F is a map from X to the set of, it is a continuous linear map from X to the set. It is called functional on the space X. X star is also, X star in fact is a Banach space. If for every f in X star, f of xn, this will become now a sequence in the set of complex numbers. We have that fxn converges to fx. Where? In the set of complex numbers. Of course, since it is a sequence, fxn becomes a sequence of complex number. Therefore, this limit has to be unique, and this depends upon x. And we say this depends upon x. We say it is f of x, right? So we say f of xn converges to fx. That means fxn minus fx mod tends to 0 as n tends to infinity. Fxn minus fx mod tends to 0 as n tends to infinity, meaning thereby that for every epsilon greater than 0, there exists some m such that fxn minus fx mod is less than epsilon for all n greater than or equal to m. Right? See, this fx in that case, sorry, we have fxn converges to fx converges to fx. This is when xn converges to weakly to x, we say x is weak limit of the sequence xn. See, this weak limit once again is going to be unique. Why it is unique? Firstly, because fxn converges to fx. Suppose xn converges to two limits x and y weakly. That means fxn will converge to fx and also fxn will converge to fy. Because all these things happen in the set of complex numbers, therefore fx is equal to fy. That means f of x minus y is equal to 0. That means f of x minus y is equal to 0 for every boundary linear functional on the space x. But then we refer to one theorem in functional analysis, that is Hahn-Banach theorem. That is, whenever we have, you see, if there is a vector x in a non-linear space capital X, such that f of x is equal to 0, f of small x is equal to 0 for every boundary linear functional f on the space x, then we have fx is equal to 0, then we have x is equal to 0. So since we are getting, if xn converges to x weakly and xn converges to y weakly, then f of x is equal to f of y for every boundary linear functional f. Then that means f of x minus y is equal to 0 for every boundary linear functional f, then on the space x. Then referring to Hahn-Banach theorem, we get x minus y is equal to 0. That means x is equal to y. That means weak limit is unique, right? So what is that we have reached? That if x is a non-linear space, and if a sequence xn converges to x and y weakly, then x is equal to y. All right. Then we come to xn converges to x strongly. This is the usual one, because this is usual one in the metric space also, because it's a metric space too. Then d of x and x tends to 0. That means xn minus x norm tends to 0, and then tends to infinity. In case xn converges to x strongly, then we say x is strong limit. The strong limit is also unique, because if xn converges to x strongly and xn converges to y strongly, then xn minus x norm tends to 0 and xn minus y norm tends to 0. Then x minus y norm of x minus y is less than or equal to x minus xn norm plus y minus xn norm. And see, right hand side is tending to 0. And therefore, x minus y norm becomes equal to 0. That means x is equal to y. That means strong limit is unique. So strong limit is unique, weak limit is unique. Xn converges to x strongly, then x is called strong limit. Xn converges to x weakly, then we say x is weak limit. But but strong limit, if xn converges to x strongly, then xn converges to x weakly also. Why that is so? Because if suppose xn converges to x strongly, and suppose f is any functional on the space capital X, then fxn minus fx modulus, this is equal to mod of f of xn minus x, and that is less than or equal to f norm into xn minus x norm, and right hand side is tending to 0 as n tends to infinity. That means fxn minus fx modulus is tending to 0 as n tends to infinity. This means fxn converges to fx. And that happens for every x. That means fxn converges to fx for every x. That means xn converges to x weekly. That means if xn converges to x weekly strongly, then xn converges to y, xn converges to x weekly also, right? So strong, we have the strong limit implies strong convergence implies weak convergence, but converse not. If xn is converging to x weakly, then xn may not be strongly convergent. For example, if we take any orthonormal sequence in a Hilbert space, no, again, I hope every participant is aware of a Hilbert space. Every participant is aware of a Hilbert space, you know. So Hilbert space, has got inner product. Um, uh, see, inner product is a map from say x cross x to the set of complex number xy going to say bracketed xy, satisfying the xy complex is equal to xy conjugate is equal to x norms the yx and xx um, uh, is equal to x norm square. Then alpha x y is equal to alpha of xy and x plus y of z is equal to xz plus y. These forms, and this is an inner product, and inner product leads to norm. That means every inner product space is going to be a non-linear space. In addition to that, if it is completeness, we have it is a Hilbert space and correspondingly a Banach space. A Hilbert space, therefore, is a Banach space always. Of course, the converse need not be, because we must have an inner product to make it, an inner product space. So there are Banach spaces, where you cannot define an inner product correspondingly. Of course, there may be inner product otherwise, but corresponding inner product may not be there. So every Hilbert space is a Banach space. Of course, a Banach space is a Hilbert space if and only if it satisfies parallelogram law. What is parallelogram law? That is x plus y norm square plus x minus y norm square is 2 times x norm square plus 2 times y norm square. Every Hilbert space is a Banach space, but converse is not true. But a Banach space is a Hilbert space if and only if its norm satisfies parallelogram law. So we have, if you take the space L2, what is the space L2? L2 space is a set of all infinite sequences which are the square of the modulus the series that is convergent. That is, it is the set of all infinite sequences over the set of complex number x1, x2, xn, satisfying sigma xn mod square and going from 1 to infinity is convergent. This is the space L2. And every Hilbert space has got, you see, a basis. This Hilbert space, particularly L2 space, the set E1, which is 1, 0, 0, the 1 at the first position, E2, which is 0, 0 otherwise, but 1 at the second position, and so on. This set En, n going from 1 to infinity, this is an orthonormal base. Well, orthonormal basis, of course, orthonormal basis means, firstly, it's orthonormal, meaning thereby that En norm is equal to 1 for all n, it is normality. Orthogonality is En Em is equal to 1 if n is equal to m and 0 otherwise. this and this is called orthonormal set. And if it is complete, means maximum, then it is a base, orthonormal base. Base is in what sense? Because every vector can be represented as each x belonging to this space is of the form sigma x en into en and going from 1 to infinity. That is why it is base. So if we consider this en, this is an orthonormal base. En is orthonormal base, and this is en norm is equal to 1 for all n, and en minus em norm is equal to under root 2 when n is not equal to m. Right? This one, uh, each x, since it is en x, xn, en, and x norm square is equal to sigma x en mod square and going from 1 to infinity. Because this is convergent, so nth term must tend to 0. That means en x will tend to 0 always. And in a Hilbert space, every functional is realized by a vector x like this. Enx tends to 0 amounts to saying that fn of f of en tends to 0 for all bounded linear functional f on this space. This means that fen tends to 0, meaning thereby that en tends to 0 weakly, but en cannot be strongly convergent because en norm is equal to 1 for all n, and therefore, because if en is to be strongly convergent, then it has to convert to 0 only as strongly, because it converges to 0 weakly, and therefore it is not strongly convergent. And but this converges to 0 weakly.